I'm Amos, and today I'm actually sharing a little bit about how we should look at future-proofing our buildings with high-performance facade. I'm a solution specialist from Technoform Asia Pacific, and Technoform, we're actually a leading partner for high-performance engineering plastic profile solutions. Quick introduction, we actually have 5 decades of know-how in terms of high precision plastic extrusion, and we focus on different industries. So from automotive, aviation, we go into cars. We also supply our plastics into Airbus, Boeing as well. But today our topic is mainly in the built environment, and we are having 2 main industries that we focus on, mainly in the insulating glass and windows, doors, and facades. In terms of, let's say, plastic profiles, I think typically people understand plastics like, general plastics. But when we move into engineering plastics, there are many things that we can actually do with engineering plastics. We can make engineering plastics stronger than metal. We can make engineering plastics as heat conductive, electrical conductive. There are many uses of plastic that can be used to establish different solutions for different industries. So for us, we basically take on any kind of challenges from our customers to come up with a specific engineering solution in the form of a plastic profile. And for Technoform ourselves, for us, we are actually a German-based company, and we split ourselves into 3 regions, based in Europe, North America, and also in Asia Pacific. I myself is based in Asia Pacific, and we have more than 45 sales sites and 14 manufacturing sites. In Asia, we actually have 3 manufacturing sites, 1 Hong Kong, 1 in Suzhou, and 1 in Singapore. I'll be talking a little bit about, let's say, future proofing. But before we can talk about future proofing, we have to talk about what are the challenges of the future. And of course, the previous speaker, IB, actually shared a lot regarding the different performance drivers of facades. But today I'll dive a little bit deeper into thermal performance and the technologies available to properly insulate the fenestration system itself. If we look at, let's say, in terms of challenges of the future, I think we currently are, let's say, facing, let's say, rising global temperature. We are actually seeing, let's say, the heat wave that's actually happening in Europe at the moment. I think UK is hitting 3 consecutive days of record high temperatures. I think IB probably could tell us later. And of course, even in South Europe, in Portugal, there's actually a drought. I think even in Singapore, we actually faced in the month of June the highest temperature recorded in the past more than 10 years. So with this, I think this is just telling us that climate change is actually happening, and we must do something about it. So in terms of facade, we need to start thinking about how to effectively reduce the heat gain coming in through the buildings itself. Number 2 is, I think, let's say all the different government agencies are actually having a lot of global carbon emission targets relating to COP targets, and they're actually setting up different targets within different industries. For example, mobility, whereby, let's say, electric cars are, let's say, the trend moving forward. Similarly, built environment, there's also targets that are being met, more tighter, more stringent building energy codes are going to be implemented through the years to 2030, even to 2050. There are also introduction of different kinds of buildings. We are talking about super low energy building, net zero energy building. So these new constructions are going to be the trends of the future. And of course, I think currently we are also facing everywhere expanding energy crisis. I think what we see in terms of the geopolitical situation around the world, and ultimately is impacting, let's say, the cost of energy. And we know that, let's say, building itself consumes about 40% energy itself. So what more should we do than start working on the building to ensure that the energy consumption gets reduced? So If you look directly into Singapore, so I'm from Singapore, so I have a little bit more data from Singapore. I'll share a little bit also in Indonesia. That in terms of total energy consumption in Singapore, if you try to break them down, generally building contributes about 31% of total energy consumption. And if we add the household elements, I think generally we are looking at about 49% of all energy consumption of Singapore. So like we mentioned, 40% globally energy consumption is coming through buildings. And envelope heat gain itself actually contributes about 7% of the Singapore total energy consumption. I think if you look into the total energy consumption of a building, if you can see my mouse here, what we have here is that the energy consumption of building is broken down into cooling, office equipment, transportation, ventilation and lighting. And cooling itself contributes about 52% of energy consumption. And I looked up in Indonesia, I think generally HVAC accounts for about 47 to 65% of total building energy consumption across different building types, hotels, commercial, residential. So different building types have a different dynamics in terms of energy consumption, but nevertheless, it is still a very, let's say, high contribution to the energy consumption. Now, if we look into the cooling load component, I think it's actually split into different parts whereby infiltration, envelope, heat gain, lights, equipment, and occupants. And in Singapore, 31% of our cooling load contributes is actually contributed by building envelope heat gain itself. Referring to, let's say, a typical building in Jakarta, I would say that typically 63% of heat gain is attributed through the office building envelope itself. So there's actually a big gap between Singapore and Indonesia. I have an analysis a little bit later, and I can share my opinion. But I'll basically, what we can see here is nevertheless, there's a big potential whereby we can work on the building envelope to actually improve the energy consumption of a building, reduce the carbon emission, and let's say create a more sustainable environment for everyone. Now, in order for us to really start to look at improving the heat gain through the building envelope, we need to understand where is the heat gain coming from. So this is a nice picture of Singapore Marina Bay Sands, and probably this office that I took the picture from is a grade A commercial building, but you think it's well designed, well catered for, properly budgeted. So the systems, facade systems are going to be great. But in reality, through the thermal imaging, I think you can see there are actually heat that are actually coming into the indoor environment. You can see the red portions of the thermal imaging is actually the portions whereby heat are coming through the aluminum framing. Okay, so this is currently the gaps that we are actually seeing in the facade. We might think through the eyes that it's a properly designed system, but actually through thermal imaging, we are seeing lots of heat entering from the external environment into the internal environment. And this is something that we need to design and cater for. Now, before I go, let's say more into it, I think first I go to a little bit more into the foundation. So we are talking about thermal performance of fenestration system in the tropics. So in terms of, let's say, thermal performance of fenestration system, I think well known, you probably know the U value and also the SHGC. U value is basically the thermal transmittance value of the overall fenestration, and then solar heat gain coefficient is of the overall fenestration. Now, these two performance indicators are actually comprised of different components. One is actually coming from the glass. This is the first component of, or a big component in terms of fenestration system. Two is actually the framing. So wherever there's a glass, as you can see in Andrea's presentation, there is always a framing. It can be aluminum, it can be steel, and of course also there's the edge of the glass. Edge of the glass is actually the interaction between the framing and the glass, and this is actually also creating certain thermal transmittance. Yeah. And generally, I would say that in terms of contribution from thermal performance, glazing contributes about 50–60%, depending on the dimension of the facade system or window system. And the framing contributes about 35–45%, and also age of the glass contributes about 5–10%. Okay. And I think generally everybody is quite familiar with, let's say, the U value and how U value is actually, let's say, gotten. I think what today I want to share a little bit more in terms of solar heat gain, because Singapore, Jakarta, we are actually more located in the tropical region, and solar heat gain coefficient is actually a very important factor that tropical climate should really start considering this parameter or this performance indicator. So generally, in terms of solar heat gain through a fenestration, I think what solar heat gain coefficient is actually basically an indication of the amount of incident solar radiation that ends up into the internal building as thermal heat. And generally, we are looking at a ratio of 0:1. Okay, of course, the lower the better. So basically, you are able to block more heat, more unwanted heat going into the indoor environment. However, there's a common misconception. The common misconception among industry people is that they commonly think that solar heat gain is only commonly used in the glazing because it's a transparent material, whereby basically incident radiation is then transmitted to the indoor. However, in reality, okay, opaque materials such as framing itself also have a transmitted solar radiation as well. So basically, they are being absorbed and then re-radiated and released into the indoor environment, as we can see in this arrow here, whereby it's actually entering as a secondary heat gain. So unlike what we commonly understand, solar heat gain is also contributed by both glass and frame. And in terms of solar heat gain through frame, there are also calculation methods whereby ISO 15099 and FRC 200 actually stipulate. So basically, this is the formula. I won't go too deep into it. Next, I would also like to go into, let's say, a heat gain mechanism through the cross-section of an uninsulated curtain wall system. So generally, we have an outdoor environment here and an indoor environment here. And what we can see here is that there is solar radiation that is actually hitting onto the external framing. Okay, and your frame is actually made up of aluminum. 95%, 90% of the curtain wall are actually made of aluminum, and the thermal conductivity of aluminum itself is about 160 watts per meter Kelvin, and this 160 times higher than glass. Glass is about 1 watt per meter Kelvin, and what it means is basically similar like wind. We actually it actually travels by the path of the least resistance. So instead of going through the glass, all the heat will actually enter through the aluminum framing, and what will happen is this thermal bridging is actually bring substantial heat into the indoor environment through the framing and causing the indoor framing temperature to rise as high as 50 degrees itself. So the problem here we're actually seeing is actually significant heat gain is coming into the aluminum frame, coming into the building through the aluminum frame. And of course, naturally, there is actually building energy inefficiency. Air conditioning has to work harder to compensate for the heat gain coming in, and ultimately there's also creating a lot of discomfort to building occupants. Imagine, just a touch of your hand on the frame, you feel 50 degrees. That's something that's not wanted. So now, in terms of facade, let's say timeline, facade development timeline in Singapore, I think we have been trying to tackle this heat gain situation since many years ago. Of course, building energy codes have been changing, but nevertheless, we have been seeing the facade development from single glazing, hard coat low E, to double glazing. Today, we are actually soft coat low E, double glazing with about U value of 1.4 to 1.7, and this is commonly adopted in Singapore. And the next question is that typically, double glazing is already, reaching its peak about 1.2. Anymore, you're going to triple glazing, you're going to have heavier system and everything. So the question is, what is the next step to improve thermal performance? So what we have here is actually cross-section, similar cross-section, but basically down here, you have a very interesting part. This is actually a polyamide. We also term it as a thermal brick. It's actually made of engineering plastic and with a thermal conductivity of 0.3 watts per meter Kelvin, so 500 times lower than aluminum. And what it actually does is that it basically reduces the amount of heat gain coming to the indoor environment. And this basically keeps the indoor surface temperature closer to the room temperature. I'll show you later some of the simulations and let's say demonstration as well. Now the question next is, a lot of time, do we really need more innovation in building facade? I think now there are definitely ways and definitely needs for, let's say, building facade to continue to innovate. But I think what we must start looking at is actually there are already a lot of proven technologies available today. And these proven technologies are actually being used in other parts of the world, not typically in the tropical region, but they are also used in, for example, in Europe, America, in China. So these are places whereby proven technologies have been used. And in the case of, let's say, thermal bricks, it has been used more widely more than 50 years ago, and is established as a good insulation solution for facades itself. And on top of that, there is also warm-edge spacers which is typically used in insulating glass, established more than 2 decades ago. So there are actually, let's say, there doesn't have to be there's a super innovative solution. There are already proven solutions that are not adopted today in our region, and these are something that we need to start evaluating and need to start discussing on whether we can use this technology in to help improve the facade performance. Of course, there are also other available solutions such as, let's say, inert gas in glazing, dynamic glazing, electrochromic, photochromic, triple glazing, maybe not so much for Southeast Asia, but there are technologies that are constantly innovating, and we can constantly keep an eye out for as well. Now, today, I think what I will also zoom in specifically is actually 2 proven facade technologies. One is actually the thermal brick technology, and the second one is actually the warm-edge spacer. So thermal brick technology, I mentioned, made of glass fiber reinforced polyamide, and have a low conductivity, thermal conductivity, and excellent mechanical strength that can be used in unitized curtain wall for up to 100 stories high as well. And what we see here is generally 2 systems. The one on the left is a non-thermally broken system. The one on the right is a thermally broken system. And what we can see after a thermal simulation, generally the U-frame value of the non-thermally broken system is about 6.5. Typically, we term this as about 7. And in terms of, let's say, U-frame with a thermally broken system is about 3.5. What you can see here is the thermal transmittance is half, almost half. And this actually reduced the amount of heat gain through the frame significantly. And the other thing I want to highlight to you is through thermal simulation, we are always looking for this wonderful rainbow line right in the middle. This rainbow line is an indication of a well-insulated system. So if you can see, if all the reds are actually kept out of the system and all the blue is always kept on the internal, basically you have a well-insulated system. Unlike the one on the left, generally you do not have this wonderful rainbow line that we can see on the right, and that is just telling us that there is a, let's say, a poor performing or a poorly designed system that does not take into the consideration of thermal insulation. Now, of course, with thermal bricks, I think basically we are able to vary the performance of the window system. What we have done is that we actually done a simulation of more than 100 available systems, and we actually did with uninsulated and insulated systems. And what we can see is that for uninsulated system, U value is approximately about 7 for windows. And generally, by adopting thermal brick, the shortest thermal break typically we are looking at is about 14.8. And what we can see is that the improvement is about 35%. And of course, if you use the wider the thermal break, and naturally you have a greater reduction in terms of the U value. Similarly, SHGC have a correlation effect as well, whereby the reduction of the SHGC when thermal break is adopted. And here are, let's say, how systems are developed, with a short thermal break you generally have a U value of, let's say, 3.5. With a 25mm thermal break, your U value can improve to 2.8. And then, of course, with a bigger, more complicated thermal break with fins and cavity breakage, you can see generally U value can actually drop to 2.0. Of course, right now there are passive house solutions that can bring the U frame down to 1.0, but these are really, let's say, more commonly used in climatic regions, very cold Arctic conditions. Yeah. Now, then we also have, let's say, curtain wall system. So generally, I would say that through simulation, the framing of the curtain wall system about 15 watts per meter square Kelvin. And by adopting thermal break, generally the improvement of U frame and SHGC about 60 to 80%. So all these actually are done through simulation itself. In fact, we moved beyond simulation. We also did some test bedding to demonstrate, let's say, thermal break insulation technology. This was an experiment done in Singapore, installation of a panel with window framings on a west-facing facade. Generally, these are thermally broken profiles and aluminum profiles placed on a panel on a west-facing facade. And what we can see here is that using different thermal breaks, so with aluminum profiles, pure aluminum profiles, non-insulated, generally the heat gain coming through is very high, as 1.1 kilowatt hour per meter square. And by using thermal break, we are able to reduce the amount of heat gain coming in through the framing itself. And on top of, let's say, reduction of heat gain through the frame, we are also able to reduce the indoor surface temperature. So what happened is that if I go back, okay, this is the external. On the internal is actually air-conditioned environment, about 25 degrees Celsius. And what happened is that you can see that the indoor surface temperature of aluminum systems is about 46 to 49 degrees Celsius. And for, let's say, thermally broken systems, it's about 32 to 35 degrees Celsius. So you can see a good reduction of heat, indoor surface temperature.
Amos, we are left with 5 minutes. Sorry.
No worries. Okay, so I'll speed up a little bit. Yeah.
Sure.
Okay, so I'll just jump. We also did another experiment, and generally this experiment was together with Building Construction Authority of Singapore, co-funded by them, and of course led by National University of Singapore. And what we did was that we actually did a testing on a 360 degrees rotating laboratory, and we are actually able to measure the heat gain through a representative day, and we can see that the heat flux reduction by using thermal break versus non-thermal break is about 60%. And of course, that was just one representative day. And what we can see here is that generally we try to do annualization in terms of the performance, and we can see that there's a 43% reduction of heat gain through the facade over the whole year itself. So I think this is also to prove that through simulation, you're also able to reduce that 30 to 50%. Even in real life test bedding, you can see heat gain reduction is actually about 40% through annualization. And this is a live test bedding done on a rotating laboratory. So what happened was that the rotating laboratory installed the facade system for 2 months, and every 2 weeks they were actually changing the orientation. So by this, they were actually getting a good, let's say, results in terms of normalization. Next, we also did, based on the test bedding, we actually did a calculation in terms of energy saving, and generally we can see that with the installation of a thermal break and the incremental cost of thermal break, generally it's not so high. Typically, it's about 5 to 10%. And what we can see is that the return on investment of, let's say, thermal break is about 3.89. I think previously, what's interesting is I actually have this slide for about, let's say, 1 year. And through this 1 year, I've been seeing this number change. So initially it was close to 5, but because of the rising prices in energy and electricity in Singapore, generally now I can see the return on investment going down to 4. So I think this is about hindsight that developers, designers, and also consultants, that we need to start to push that, you know, at the end of the day, limited resources are in the world. There are limited resources in terms of energy and everything. So what we need to do is that we need to start to design right, so that we don't have to, feel the wrath of what we designed 20, 30 years later. Now, the next technology that I'll touch on is also it's actually the thermal H-bond solutions for the insulating glass. Typically, double glazing actually requires the use of a spacer, and a traditional spacer is made out of aluminum. Similarly, aluminum is 160 watt-meter Kelvin, and for Technoform, we actually have a co-extruded hybrid warm-edge spacer, which is actually made of polypropylene and stainless steel. And generally, what we are able to do is that we are able to improve the equivalent thermal conductivity by 10-20%, 10-20 times itself. So, and on top of that, if you were to look at, let's say, the true performance of a warm-edge spacer, is like by replacing an aluminum spacer with a warm-edge spacer, immediately you are able to improve the U value of the system by about 10-15%. Yeah, so this is actually a very simple swap and change kind of replacement to improve the thermal performance of the system itself. Now, okay, so I've talked about technology. I think I also just want to have a short emphasis in terms of durability and lifetime. I think this is actually very critical. Generally, buildings are designed are built and designed for maybe 50, 100 years before they are torn down. In Asia, unfortunately, it's shorter, but of course, the trend is that we are moving to longer lifetime. And this means facade have to start to be more durable. For Technoform, in terms of our product, we actually have all these solutions meeting global standards from American to European standards as well, ASTM, AMA, EN, and generally for thermal bricks, we have standards for thermal barrier and also for warm-edge spaces as well. On top of durability, I think the other part is catchphrase for everyone is sustainability. And I think what's important is everything goes in a circle. I think we have to look at the entire product life cycle. And for us at Technoform, I think in terms of all the product solutions, we have always been trying to push our sustainability core, and our products are actually Cradle to Cradle Gold certified. And also Passive House certified for the warm-edge Singapore Green Building product certified as well. And we are also listed in the super low energy building database for Singapore for both solutions as well. Now, to summarize, generally, I have 4 key takeaways. Commercial facades are typically using high performance glazings, but there is actually still significant heat gain that's coming through the aluminum frames and edge of glazing. Number 2 is there are actually existing and proven technologies in the market, and we can actually tap on this to design high performance facade. On top of that, durability and lifetime performance are always an important factor when designing for facade. So always look for materials that give you the kind of, let's say, proven lifetime and durability assurance. And of course, let's say, I hope with all this that I mentioned, I think high performance facade are actually key towards future proofing our buildings. So yeah, we need to design for high performance facade for future proofing. I'll just run through very quickly. These are some of our partners and project references. These are different window fabricators and facade fabricators that we work with. So some of these names you're probably very familiar with. And also some of the glass companies that we work with as well globally. Some project reference, Beijing Citic Tower, LEED Gold certified, tall building, triple glaze, unitized curtain wall system. Taikang Tower, Beijing, amazing 17 meters tall insulating glass using our Technoform warm-edge spaces itself. Got a Guinness World Record under North Glass. Opus Dubai, very nice A-class energy rated building with very beautiful curvatures. So basically we had to work with the fabricators to come up with special curvatures, special way to deal with the curvatures while ensuring thermal optimized solutions. Yeah. Then closer to home, we have Thailand. You see residential buildings that are already using, let's say, thermal break solutions as well. In Singapore, Holiday Inn Express hotels that are using. And what's interesting is that this is actually a project that's about 7-8 years ago. And in fact, the developer came back to us and said that actually the return investment for hotels are actually faster, 3 years, because air conditioning for hotels have to be on 24/7. So the return on investments is actually faster for hotels itself. And finally, our recent project, PSA Transport Terminal. This is actually a super low energy building under the transport itself, and it's adopting both SLEV smart hub technology of warmage and thermal break. So I think that's all for my side. I hope I didn't go too fast. Yeah.